Good afternoon, everyone. In this section, we're going to take a look at section 7.4. Section 7.4 covers the double angles formulas or identities, double angle identities, the half angle identities, and we have product to sum and sum to product. Identities. Before we get started, I did want to call you guys' attention to it so you guys know where to find it. Some online resources so that you can have tutorial services. If you go to the main menu and click on student support, come down here and look at tutorial services. And we're going to look for the math lab. Click on the math lab one, and it tells you what to do to how to sign up for online tutoring for the math lab. Okay. I've also listed a link to the MESA flyer. That's where all the engineering and calculus and physics students hang out. They have online tutorial services as well. And anyone that's capable of teaching calculus is more than qualified to go over trigonometry with you. So those are other resources to use as well. But let's take a look at what's going on here. And let's just dive on the last section, 7.3, sum and differences. We started off with cosine. Let's start off with cosine here. So the double angle formula is cosine 2 theta. And I can write that as cosine of theta plus theta. And we can use the rules that we had for cosine of A plus B. This is cosine theta minus sine theta. That was the identity for cosine of A plus B, which is cosine squared theta minus sine squared theta. This is the first one of three. We have two more, and to find the other two, we will use the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. I can write that two ways. If I subtract sine squared theta from both sides, I have that. And if I subtract cosine squared theta from both sides, I have that. Let's plug those into the first equation. So cosine 2 theta equals 1 minus sine squared theta minus sine squared theta. And we can gather like terms. We get cosine of 2 theta equals 1 minus 2 sine squared theta. This one's handy when you only have sine theta. You don't need to find cosine theta to work with it. It's good stuff. Let's take a look at the other version. I'll use that one now. Cosine of 2 theta is equal to cosine squared theta minus 1 minus cosine squared theta. And what we end up getting, if we distribute that minus sign, the minus to the 1 gives us a -1. The minus to the minus cosine squared gives us positive cosine squared. And we're going to add cosine squared to cosine squared. We get 2 cosine squared theta minus 1. So this version of cosine 2 theta is fantastic when you don't have sine theta. You don't need to calculate it. You can just use this. Let's take a look at sine formulas now. Hit pause if you need this up longer. So sine of 2 theta is sine of theta plus theta. And we'll use the same formula as we had for sine of a plus b. This is sine of a cosine b plus cosine a sine b, where a equals b equals theta. These are the same thing. Sine times cosine is the same as cosine times sine. So we can rewrite this as 2 sine theta cosine theta. Now, sine of 2 theta and cosine 2 theta, you will use a lot. It's extremely used in calculus and a lot of stuff like that. It always comes up. Tangent 2 theta, not so much, but you need to know what it is. And we're going to derive it the same way we've done the other ones. Tangent of 2 theta is the same thing as tangent theta plus theta. And what does that equal? That's tangent of theta plus tangent of theta over 1 minus tangent theta, because A and B are again both theta. So tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. So that's our tangent one. I'm going to put our sine and cosine so it's all on one page for you. We had sine of 2 theta up above. It's 2 sine theta cosine theta. And then we have our 3 flavors for cosine of 2 theta. Cosine of 2 theta equals cosine squared theta minus sine squared theta, or 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. You should memorize all of those. Again, tangent's the one you'll use the least, but you should know it. And how can we use this? If you need this up longer, pause your video, take down the notes you need. So in this example, we are going to find functions of 2 theta given theta. It's off screen, my bad. All right. So we are given sine theta equals -4/5 and cosine theta is greater than 0. We want to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Again, we can use the Pythagorean formula. We could work with sine squared theta plus cosine squared theta equals 1 because we have sine of theta. That's one option. Or we could take a look at sine theta. Where is sine negative and cosine is positive? Sine is negative and cosine is positive down here. So that's our reference angle theta. And sine of theta is y over r. Y is negative here. R is always positive. And this is x. And our other option, option B, x squared plus -4 squared equals 25. Since I put this one up last, I'll just work through it. X squared plus 16 equals 25. You subtract 16 from both sides, we get x squared equals 9. And this should give us x equals plus or minus 3. But we're in quadrant 4, x is positive here, so x equals 3. So the things I need for sine 2 theta, cosine 2 theta, and tangent 2 theta are what sine, cosine, and tangent are. Let's just jot those down. Sine theta was given. Cosine theta is x over r, which is 3 over 5. And tangent theta is y over x, which is -4 over 3. Now that we have that, we can start figuring out what we have. So sine of 2 theta, that was first task. That is 2 times the sine of theta times the cosine of theta. We will replace that with the values we have, -4 over 5 and 3 over 5. And if you multiply that all out, you're going to get -24 on top and 25 on bottom. Cosine 2 theta, we got some options. If we do the default one we started with, cosine squared minus sine squared is 3/5 squared minus -4/5 squared, which gets us 9 minus 16 on top, which is -7 over 25. We can do tangent of 2 theta a couple ways. Let's do the formula. This was 2 tangent theta minus over 1 minus tangent squared theta. Two times negative 4/3 over 1 minus tangent squared is negative 4/3 squared. This is negative 8/3 over 1 minus 16/9. We get a common denominator, it will be 9 over 9. Let's write that as 9 over 9. And I get negative 7/9 on bottom. And this turns into division by a fraction is the same thing as multiplication by the reciprocal. The negatives go away. The 3 and the 9 simplify a little bit. And I get 24 over 7. Of course, the other way to get tangent 2 theta is it's sine of 2 theta over cosine 2 theta. And you just pull those down and use them. And you'll get the same thing. Any questions on that? All right, let's take a look at another example. Last time we found functions of 2 theta given theta. Let's switch it around. Now let's find functions of theta given 2 theta. Here's our example. Theta is between 180 degrees and 270 degrees. And cosine of 2 theta is negative 4/5. Find the 6 trig functions of theta. All right, let's reason some stuff out real quick. What is this piece of information telling us? It's between 180 degrees and 270 degrees. That means theta is in quadrant 3. We're down there. What do we know about quadrant 3? We know sine of theta is less than 0 and tangent theta is greater than 0. So we should end up with negative sine and positive cosine. What about cosine? Negative sine, positive tangent. Cosine's also negative down there. So what can we do? Well, we've got cosine 2 theta. It's got a couple forms. I know it equals -4/5, but it also equals 1 minus 2 sine squared theta. So I'm going to rewrite this 1 as a 5/5 so that I can subtract it over. If I subtract it over to the left, we have -4/5 minus 5/5 is -9/5. And that equals -2 sine squared theta. We divide by -2 or multiply by -1/2. And I get 9/10 equals sine squared theta. Take the square root of both sides. Sine theta, I know it's negative because it's quadrant. Square root of 9 is 3, and we've got √10 on bottom. And if we want to write that properly, we'll multiply top and bottom by the denominator. This will give me cosecant right away if I flip that over. Cosecant theta, let's just flip over the top one. I've got -√10 over 3. All right, so we've knocked out 2 of them. Let's take a look at what that thing's telling us pictorially. That's my theta hat. If I use this one up here, y over r, this is -3 over √10. And I can find out x. X squared plus -3 squared equals 10, radical 10 squared. X squared plus 9 equals 10. X squared equals 1. We're in the quadrant 3. We take the square root, we get x equals -1. And now that we've got that, we can use our picture to find the other 2. Or the other 4. So cosine of theta is x over r, which is -1 over √10. So cosine theta is -√10 over 10. Oh, my picture's getting all rotated, but my bad. I need better lighting in here. We can do secant theta just by flipping that one over. This is -√10. And tangent theta is y over x. -3 over -1 is +3. That's tangent theta. And of course, the reciprocal is cotangent theta, 1/3. Yeah, I'm working from home, and I still got my cosine College of Sequoias shirt on. Awesome. It's not a cosine shirt. That's great. All right, I'll assume you're done with that one. There's some other stuff we can do with this stuff. We can simplify expressions. Sometimes this requires a little thinking. Sine of 75 degrees, cosine of 75 degrees. So which of those recent formulas does this look like? This actually looks a lot like, well, if A equals B equals 75 degrees, this looks like sine of 2 theta equals 2 sine theta cosine theta. The problem is we don't have this 2 in front. The way we can compensate for that, if I want to just end up with sine theta cosine theta, I can multiply each side by 1/2. This is actually related to the product to sum and sum to product identities. We're going to do in a little bit. But that means in my problem, I can say this is 1/2 of sine of 2 times 75 degrees. Which is 1/2 of sine 150 degrees. That's 150. My reference angle is 30 degrees. The reference angle is 1/2 for sine. Sine of 30 is 1/2. In quadrant 2, sine is also positive. So sine of 150 equals 1/2 times 1/2, like that, and we end up with 1/4. One minus 2 sine squared of 3x. Let's simplify that. So if I say theta equals 3x, this looks like 1 minus 2 sine squared theta. And from our formulas, we know that's cosine of 2 theta. Now let's put theta equals 3x back in. Cosine of 2 times 3x is cosine of 6x. Ready for more? So here we're going to write cosine 4x in terms of only cosine x. So hopefully you pause this and think, how can I do that? What information have we had in the past? One thing we could do, I could say this is 2x plus 2x. Which means cosine 2x minus sine 2x sine 2x. And what is each one of these? So cosine 2x, I want it in terms of cosine x. Let's look at the equation that had cosine x in it for cosine 2x. This piece turns into 2 cosine squared x minus 1, and so does that piece. Then we've got minus, this is 2 sine x cosine x times 2 sine x cosine x. We're getting closer. We don't want the sine x's. So let's clean this up. If I distribute, I have 4 cosine to the 4th x minus 4 cosine squared x plus 1 minus 4 cosine squared x sine squared x. If I look at these two both have a negative 4 cosine squared x in there. Can we do anything with that? I'm going to move the other ones that don't have the red underline in front. I'm going to factor out that negative 4 cosine squared x. If I take it out of the first one, I have minus 1 or 1. And I take it out of there, I have sine squared x there. Something's off. Hold on one second. That's plus. That doesn't look like it's helping me any. So let me try something else. Not a big help. Let's go back a line. How about instead we rewrite sine squared x as 1 minus cosine squared x? That's from our Pythagorean identity. And now look, everything's in terms of cosine x. So sometimes the first thing you try doesn't work. Don't let that discourage you. Just realize that's taking me somewhere that's not helping. I don't have a formula for 1 plus sine squared x. So maybe I should take a different route. I'm going to distribute there. So we've got cosine 4x equals 4 cosine to the 4th x minus 4 cosine squared x plus 1. Then I'll distribute that minus 4 cosine squared x and plus 4 cosine to the 4th x. And we can gather like terms. I've got a couple things of like terms. I've got two sets of cosine to the 4x. They're both 4s, so add the 4s together, I get 8. 8 cosine to the 4th x. I've got a couple cosine squared terms. Combine those, I've got minus 8 cosine squared x. And finally, all I have left over is the plus 1. Any questions so far? Email me, because I know it's not a live chat right now. So we're going to do half angles last. They stem from the following problems. Let's take a look at the product to sum identities. I'm going to be honest with you. Even if you flashcard them, you are only going to remember them this semester, and you will unlikely to have them retained long term. It's more important that you actually understand how we get them. If you remember how we get them, you don't need to memorize the complex formulas because it stems from formulas you already have. So let's take a look at deriving them. I'll be honest, if you memorize them now, it'll be good for the exam. Will it? I don't think these are that important to have memorized because you really won't retain them. You won't. It's unrealistic. And you'll see why. They're long, they're complicated formulas. But they're easy to come up with. Check this out. So I've got cosine of A minus B. That equaled cosine A cosine B plus sine A sine B. And I have cosine A plus B, cosine A cosine B minus sine A sine B. Those are our sum and difference for cosine. Add them. If we add them, I get cosine of A minus B plus cosine of A plus B. Well, look what happens here. I've got 2 cosine A cosine B and the sine A's and sine B's cancel each other out. And so the way they end up doing this, they multiply both sides by 1/2. And this is called the product of sum. We start off with cosine A and cosine B. It's equal to 1/2 the sum of cosine A minus B plus cosine A plus B. You're not going to memorize that. That's just one of them. There's 4. There's 4. What else could we do? We could I'll put a box around that. We could also subtract them. If I try that, I get cosine of A minus B minus cosine of A plus B. Now the first two cancel out, and I have sine A sine B minus a minus sine A sine B. This is 2 sine A sine B. So this leads us to the other one, or one of the other four. Sine A sine B equals 1/2 the cosine of A minus B minus the cosine of A plus B. If you practice writing out this derivation, you'll do it a few times, you'll remember how to do it. Because all it took to do these is to remember cosine A minus B and cosine A plus B. And those are important to memorize. Those are easy enough to memorize that you should memorize them. If you don't memorize them, you are going to have a really, really hard time in calculus. The same thing goes with the sine ones. So that's 2 of them. You want to look at the other derivation. We do sine of A plus B and sine of A minus B. Sine A cosine B is in front of both. Then the signs switch. And this leads to the following two. If we add them, these two go away. And we're left with 2 sine A cosine B. And we get sine A cosine B is equal to 1/2 sine of A plus B plus sine of A minus B. And if we subtract, we're going to have minus 2 cosine A sine B. So when we divide by -2, it might be easier to subtract them in the opposite order. Do sine A minus B minus sine of A plus B. So we're subtracting the top row from the bottom row. These two cancel out. Cosine A sine B minus a minus cosine A sine B is 2 of them. Then we divide by 2 and we have 1/2. What the hell did I do? I have these signs backwards. So I didn't need to change the order of that. Oops. Get going so quick, it's easy to drop the ball. It's important you do the homework on this. It's important you have practice using them. I'll show you why. In fact, let's just show you why right now. Where does this come up in calculus? This is used a lot in calculus. And where it pops in, finding integrals is difficult when they are products. And much easier as a sum. This shouldn't mean anything to you yet. But for example, that's the integral symbol. If I have sine of 5x cosine 4x, that's hard to do. It is much easier when these are addition. So this is sine cosine. Here A is 5x, B is 4x, and I'm going to use the sine A cosine B one. This is equivalent to 1/2. It goes outside the integral sign, as you'll learn. Sine of A plus B, sine of 5x plus 4x, plus sine of 5x minus 4x. And when you start doing integrals, you'll see how easy these are to do. And you will find out quickly how hard those are to do. This is done almost instantaneously once you learn the rules. It's really simple. It's one of the easiest integrals to do, both of them. That's where it pops in. Are you going to remember that? Are you going to remember all those identities? I can't say I did, but I remember they existed. Even when I went from trigonometry into pre-calculus and then into calculus, there was a longer sequence when I took the course here. By the time I got to calculus, the product to sum identities just didn't stick. But I knew they existed, and I knew when I saw one that this is applies, and go work out what the formula is again. And I practiced doing that because on an exam, you're not going to have a cheat sheet in front of you. You need to be able to come up with the formulas. They're not that hard to come up with. All they require you to know is cosine of A minus B, cosine of A plus B, sine of A minus B, and sine of A plus B. Four equations. We can do an example with this. I'm not testing you on this, but I want you to work with them, played with them. The double angle identities, I'm testing you on. Those are vitally important. The sum and difference formulas are vitally important. These product to sums and sum to products, you're better off knowing how to come up with them because it's easier to know that than to try to memorize some obscure formula. So 6 cosine 55 degrees, cosine of 35 degrees. Which formula does this look like? This looks like cosine A, cosine B. Looks like that one right there, right? Except I have 6 of it. So if I want 6 of them, I can write that as 6 times 1/2. If I say A is 55 degrees and B is 35 degrees, I have cosine of A minus B plus cosine of A plus B. So the 6 times the 1/2 hits it right away. I've got 3 times cosine of 20 degrees plus cosine of 90 degrees. And what's the cosine of 90 degrees? 0. So this just simplifies to 3 cosine of 20 degrees. All right, so the sum to product. So let's start off with one of our product of sums. This isn't as easy to memorize, but it's actually a really good skill. You'll do this a lot in calculus as well. So let's start off with cosine A sine B. And that was 1/2 sine of A plus B minus sine of A minus B. And I'm going to do a couple things. I'm going to say the letter U is A plus B. And the letter V is A minus B. These are called making a substitution. It's a useful skill to start developing. You will do a lot of substitutions in calculus, a lot. In fact, oftentimes they help you in algebra and all sorts of stuff. So if I add together U plus V, I get A plus B plus A minus B. The B's cancel out, that's 2A. So A equals U plus V over 2. If I solve for A right there, Now let's look at u minus v. This equals 2b. And this tells me b equals u minus v over 2. So let's take those and let's take those and plug them back into either side of the equation, wherever they pop up. Cosine A is cosine of u plus v over 2. B is sine B is sine of u minus v over 2. Then I have the right side is 1/2. A plus b is u, so this first thing is just sine u. And a minus b is v, and this is just sine v. If I put this stuff on the left, I've got sine of u minus sine of v multiplied by 2 to get it on the other side. I've got 2 cosine of u plus v over 2, sine of u minus v over 2. And now, this is a little hand wavy. We're going to do a different substitution going back. Let u equal a and b equal b. And I get sine of a minus sine of b equals 2 cosine of a plus b over 2 sine of a minus b over 2. This is far less helpful in calculus, to be honest. It's easier just to work with the left side. If you've got sine A minus sine B, the integrals and derivatives work fine just the way they are. And switching to making a product actually makes the problem harder. So you will not see these hardly ever. Okay. But I'll give you the other ones. That was sine of A minus sine of B. If we do sine of A plus B, or sine of A plus sine of B, when you work that out, you get 2 sine of A plus B over 2 cosine of A minus B over 2. And if you do need these in calculus, it'll be on like a homework problem, and you can always Google these formulas. You just got to know what to look for. And if you do some homework problems using them, you'll get some practice in. So that's sine A minus sine B and sine A plus sine B. And you notice it just switches whether we use cosine or sine on the positive one or to the negative one. The cosine ones, we've got 2 times cosine. Both of these are cosine functions. One's the positive, a plus b. One's the minus 1, a minus b. And cosine of a minus cosine of b, when you work it out, is actually negative. It's a negative 2. And then we have sine of a plus b over 2, sine of a minus b over 2. And you're just doing those u substitutions and v substitutions we did earlier. Again, These are called the sum to product. And they are far less useful. Ready for an example? I'll leave this up there while we work on them. Work on an example. Let's write cosine of 5 theta plus cosine of 3 theta as a product. Looks like we're using this one right here. A equals 5 theta, B equals 3 theta, and I've got cosine A plus cosine B equals cosine 2 cosine of A plus B over 2 cosine of A minus B over 2. And now let's plug in the 5 theta and 3 theta. Five theta plus 3 theta over 2, and then 5 theta minus 3 theta over 2. We have 8 theta divided by 2, that's 4 theta. 5 theta minus 3 theta is 2 theta divided by 2 is just theta. So that's the sum written as a product. And now let's talk about the half angle identities. So this is how you do it. You work with the double angle formulas. So work with the double angle formulas. And then replace 2x with a, which means x equals a over 2. And I'll show you what I mean. So we had cosine 2x. Let's just take a look at cosine 2x. We know that equals 2 cosine squared x minus 1. I'm going to solve for the cosine squared x. So I'm going to add 1 to both sides, and I get cosine of 2x plus 1 equals 2 cosine squared x. I'm going to put it on the right because I'm solving for this. I kind of like having it over there. So when I divide by 2, I get cosine squared x equals cosine of 2x plus 1 over 2. And I take the square root and I get cosine x equals plus or minus. Oftentimes we put the 1 in front just to make it clear it's not part of the cosine. And now 2x equals a, and x equals a over 2. Cosine of a over 2 equals plus or minus the square root of 1 plus cosine a over 2. That's one of the half angle formulas. It's the cosine half angle formula. And usually they leave it like that. They don't rationalize, get rid of the radical on the bottom and put it on top. They just leave it like that. Because oftentimes you have cosine A and you're trying to find out what half of that angle is. Hit pause if you need that up longer. The sine 1 actually comes from cosine 2x as well. If I move the 2 sine squared x over, it becomes positive. If I subtract the cosine 2x, it becomes negative. If it takes you a second and you need to work that out in a couple steps, please do so. And this means sine squared x is 1 minus cosine 2x over 2. And we take the square root of both sides. And we make the same substitution. Sine of a over 2, or another way of saying that is 1/2 a, equals plus or minus the square root of 1 minus cosine a over 2. That's the sine half angle formula. And finally, let's look at tangent. So tangent of a over 2, well, that's sine of a over 2 divided by cosine of a over 2. And we get 1 minus cosine 2, or cosine a over 2 on top, with a radical of 1 plus cosine a over 2 on bottom. We multiply top and bottom by a radical 2, and it'll clear it out, simplifies it up. Tangent of a over 2 is plus or minus the square root of 1 minus cosine a over 1 plus cosine a. So that's one form. Another thing they do, they clear the radical. So they multiply top and bottom by 1 minus cosine A. This becomes plus or minus the square root of 1 minus cosine A squared over 1 minus cosine squared A. And that's under a radical as well. This top thing is just 1 minus cosine A, though. The radical and square clear. 1 minus cosine squared is sine squared. And so you get 1 minus cosine A over sine of A. So that's another option. And the other option is or multiply the top and bottom by 1 plus cosine A. And that'll get you this second flavor. If you do that, the top ends up being sine A. And the bottom ends up being 1 plus cosine A. And we also have, so plus or minus on all these. Or you have the one that just has cosines in it. For me, I very much consider the half angle identities in the same realm as the product to sum and sum to product. Once I got to calculus, I didn't use them hardly ever at all. And it was easier to look up how to do it and remember how to do it, go through this process of solving for them, than to memorize these formulas. I can remember the general outline. I know the cosine half angle and sine half angle have a square root, and I know there's a cosine A in it, but the exact form, I have to work it out. And it all starts with cosine 2x. Okay. Well, that's it for the material for section 7.4. I'll get this uploaded tonight. I'll try to get a couple more up for you tomorrow. And we'll have a bunch up. Well, I'll have all of chapter 7 up by early midweek. Maybe Monday if I'm lucky. All right. Peace. And we'll end the meeting.